All right, this is our walkthrough for the homework assignment titled Equations of Tangent and Normal Lines. So first homework assignment of the applications of the derivative unit. So we're first asked to just find the equation of the tangent line to this function x over 1 plus x squared at x equals 3. So to write the equation of the tangent line, we need both a point and we need a slope, so that we can write the equation in point-slope form. I think on my answer key I converted them all to slope-intercept form, or at least some of them, but that's not ever necessary. You can always just leave it in point-slope form. So we're going to do that here on this walkthrough. So first of all, we can just find what the value of the function is at 3. So in order to do that, we'll just plug in 3. That's going to give us a 3 in the numerator and 1 plus 3 squared, or 3/10 in our as our full thing, right? 10 in the denominator. So our point that we're going to be using is the point 3 comma 3/10. And then we're going to find our derivative, right, y prime. And in order to do that, since it's x over 1 plus x squared, we're going to use the quotient rule. So that'll be 1 plus x squared times the derivative of x, which is just 1, and then minus the x times the derivative of 1 plus x squared, which is 2x. And then we'll divide all of that by 1 plus x squared squared. And if we simplify that down just a little bit here, I think we can see that that's 1 plus x squared and then minus 2x squared. So that'll be 1 minus x squared over 1 plus x squared squared. And we can then just go ahead and evaluate that at 3. So if we plug in 3 to that, we have 1 minus 9 in the numerator. And in the denominator, we have 10 squared. So that'll be negative 8 over 100, which just simplifies down to negative 2 over 25. So that's our slope for our tangent line. We've got the point. Now we just have to plug it into point-slope form. So we remember that point-slope form is y minus y1 equals m times x minus x1. So we've got y minus 3/10 equals negative 2 over 25 times x minus 3 when you plug in your point and your slope. And that's our answer to our first one. And again, I think I said on the answer key, I definitely converted it into slope-intercept, but that is not ever necessary, so don't worry about doing that. All right, for our next one, same basic question. Find the equation of the tangent line, 2x over x plus 1 at x equals 1. So first we'll figure out what y of 1 is equal to. Well, that'll be 2 in the numerator. 2 times 1 is 2. Right? And in the denominator, we'll get 1 plus 1, which is also 2. So the point we're looking at is the point 1 comma 1. Then we will use the quotient rule to find our derivative. So we'll do our denominator, x plus 1, times our derivative of 2x, which is just 2, so v du, minus our numerator 2x, times our derivative of x plus 1, which is just 1. And then we'll divide that all by our denominator squared. And if we simplify that down, the x times the 2 is 2x, and when we subtract this 2x, that'll cancel. So we're really just left with a 2 in the numerator there. So we've got 2 over x plus 1 squared. And if we evaluate that at x equals 1, well, that's just going to be 2 over 2 squared, or 2 over 4, which is 1/2. And so once again, we'll use point-slope form here. We'll just write y minus our y value, which is 1, equals 1/2, our slope. And then we've got our x minus our x value, which is just 1. So, and of course, if you want to convert it to slope-intercept, go ahead, but not necessary at all. Okay. For our next one here, y equals x plus root x at x equals 4. We're again just looking for our tangent line. So we'll evaluate this at 4 first. So y of 4 is equal to 4 plus the square root of 4, which is just 6. So the point that we're looking at here is the point 4 comma 6. And then we'll take our derivative. So y prime is going to be 1 plus 1 over 2 root x. And if we evaluate y prime at 4, that gives us 1 plus 1 over 2 root 4. Well, that's 1 plus 1/4, which is 5/4. So using point slope form, we get y minus 6 equals 5/4 times x minus 4. For our next one here, we're just going to do, again, the same thing. We're going to first find what y of 2 is. So we've got y of 2 ought to be 1 plus 2 times 2 is 4. And then we'll square that. So 1 plus 4 is 5. And when we square 5, obviously we'll get 25. So the point we're looking at is the point 2 comma 25. And then we need to find our derivative. So this is going to be y prime, and we can see that's u squared. We have two options. One is to just call it u squared and use the chain rule on it with the power rule. The other is to just distribute it out. It doesn't really matter which way you do it. I'm going to just use the chain rule, so it's 2 times u, right, because it goes from u squared to 2u, and then we multiply by the derivative of the u, which is our 1 plus 2x. That derivative is just 2. If we evaluate that at x equals 2, then we have 2 times 5 times 2, which is just 20. And so we are, when we put that into point slope form, going to just get y minus 25 equals 20 times x minus 2. And that will be our final answer. Alright, for our next one here, we're going to show that this curve has no tangent line with a slope of 4. So first off, we have to get a function that represents the slope of the tangent line. So we'll do that by taking the derivative. So y prime will be 18x squared plus 5. And then we want to show that this is never equal to 4, right? So we'll just set this equal to 4 and see what happens. So if I set this equal to 4, we end up with 18x squared equals negative 1, or x squared equals negative 1/18. Well, we know that that has no real solutions, and therefore there is never an instance when our function is going to have a tangent line with a slope of 4. Alright, for our next one here, we're going to find the equation of the tangent line and the normal line to this function at the point 1, 1. And then we're also going to find the x values for when the tangent line is horizontal. So to start off with, we've already got the point, so we don't need to do any plugging in to find that. But we'll start off with finding our derivative. Right? And so y prime is going to be, since that's u to the 10th, it'll be 10 u to the 9th times the derivative of u. The derivative of 2x minus 1 is 2. So to find the slope of the tangent line, we're going to want y prime of 1, which will be 10 times 1 to the 9th power times 2, which will just be 20. So that's the slope of our tangent line. And then the slope, in fact, we'll write that there, the slope of our tangent line. And that means the slope of our normal line, since the normal line is the line that is perpendicular to the tangent line at this point, its slope will just be the opposite reciprocal of that. So we'll flip it to make it 1/20th, and we'll take the opposite to make it negative 1/20th. So our tangent line equation is going to be y minus 1. That's our y value here in our point, equals 20. That's slope times x minus 1. Okay, that's the tangent line. And our normal line is going to be y minus 1 equals negative 1/20th times x minus 1. No real difference there other than we're just using that other slope. And then the last question here is to find the x values for which the tangent line is horizontal. Well, the tangent line would be horizontal when that derivative, which simplified down is 20 times 2x minus 1 to the 9th power, is equal to 0, right? Because a horizontal line has a slope of 0. Well, that'll only happen when 2x minus 1 equals 0, or when x equals 1/2. So that's the x value for when we have a horizontal tangent line here for this function. All right, our next one here is it's asking us the same thing that the previous question was asking, right? To find the tangent line and the horizontal or the normal line at that point. This time it's -1√3, and then also to find any x values when our tangent line is horizontal. So step 1 is just going to be take our derivative. That's going to be a chain rule derivative. Right? So y prime is going to be 1 over 2 root 2x squared plus 1, because that's 1 over 2 root u. And then we're going to multiply by the derivative of 2x squared plus 1. Well, that's going to be 4x. So if we simplify that down just slightly, we end up with 2x over root 2x squared plus 1. Okay. So from there, we're just going to plug in the x and the y values, or just our x value, sorry, just that -1, to find what our slope of our tangent line is. So we'll start off with y prime of -1, which is going to be a -2 in the numerator. And then in our denominator, it's going to be a square root of, well, let's see, -1 squared is 1. If we multiply that by 2, that's 2. And if you add 1, that's 3. So that slope is going to be -2 over root 3. Right? And that's the slope of our tangent line, which means that the slope of our normal line is just going to be the opposite reciprocal of that, positive root 3 over 2. So as we write those two equations, the tangent line will be y minus our y value of root 3 equals -2 over root 3 times x minus -1, which would just be x plus 1. Then our normal line will be y minus root 3 equals positive root 3 over 2 times that same x plus 1, using that same point, just with the normal line slope. And then lastly, we want to know, when does this have a horizontal tangent line? Well, a fraction equals 0 as long as the numerator equals 0, but the denominator does not. So really all we need to do is set 2x equal to 0, which gives us x equals 0. And then we'll plug that value in to our denominator of our derivative to make sure it doesn't make it 0. And I think we can clearly see that that becomes the square root of 1, which is 1. So it does not make that 0. So that's okay. And we can also see that x equals 0 is in the domain of our original function, right? Because I can plug 0 into that. And therefore, x equals 0 is the x value at which we have a horizontal tangent line for this function. For this one, we're going to, again, find the equations of the tangent and normal lines to the function at a given point. And then we're going to find the x values when we have a horizontal tangent line on the interval 0 to 2 pi. So we'll start off with, again, just taking our derivative. So y prime is just going to be 2, and then the derivative of cosine 4x is going to be a minus a sine 4x, and then we're going to have to multiply that by the derivative of 4x, so that'll be minus 4 sine 4x. And we'll evaluate that when x equals 0. Well, that's just 2 minus 4 times the sine of 0, which is 0. So our slope of our tangent line is going to be 2. And then our slope of our normal line will just be the opposite reciprocal of that, which will be -1/2. So our two equations for the tangent line will be y minus our y value of 1 equals our slope of 2 times x minus 0. And of course, that one's pretty easy to see. We could have also just done slope-intercept form, y equals 2x plus 1. And our normal line should be y minus 1 equals -1/2 times x minus 0. Or if you want to put that one in slope-intercept, since we're already given the y-intercept, so not a big deal to do that. It's just -1/2x plus 1. Then the second part of this is to figure out the places where it has a horizontal tangent line on that interval. So we'll need to take our derivative, which is 2 minus 4 sine of 4x, and set that equal to 0. We're probably going to need another page for this, but we can see that'll give us 2 equals 4 sine 4x, or sine of 4x is equal to 1/2. So let's do a little bit of extra work here on a separate page here. We need to solve the sine of 4x equals 1/2, and we need to do that on the interval from 0 to 2 pi. Okay? So when we do that, we know that sine is equal to 1/2 at 2 different values normally. Right? So we basically need to say that whenever 4x, whenever that angle is equal to pi over 6, that ought to give us a value of 1/2. Right? But that happens every 2 pi times any integer. So this is one possibility, right, where our angle is pi over 6 plus 2 pi n. The other possibility will be an angle in the second quadrant that has the same reference angle as pi over 6. That'll be 5 pi over 6, because we know that sine is also positive in the second quadrant. So we end up with 4x equal to 5 pi over 6 plus 2 pi n. Simplifying each of these gives you x equals pi over 24 plus pi n over 2, and x equals 5 pi over 24 plus pi n over 2. And so now all we have to do is we have to go in and evaluate this for values of n, where n is any integer. And I think we can see, since we're looking at the interval from 0 to 2 pi, when we do this, we can plug in 0 for n, we can plug in 1 for n, 2 for n, 3 for n, but once we plug in 4 for n, this term here in each of them, if n is 4, becomes 2 pi. And then we have something plus 2 pi, so we're going to be outside of our interval. So really all we want is n to be 0, 1, 2, and 3. So when n is 0, we end up with pi over 24 here. When n is 1, we end up with pi over 24 plus pi over 2. Well, pi over 2 is 12 pi over 24, so that'll be 13 pi over 24. And then when we add the next one, which is when n is 2, that's going to end up giving us 25 pi over 24. And once more, when we put in a 3 for n, right, 3 pi over 2, well, that's going to give us 36 pi over 24 plus 1 pi over 24 is 37 pi over 24. And on the other side, we'll have the same things here going. When n is 0, we get 5 pi over 24. And each time we're just adding half of a pi, or we're adding 12 pi over 24. So when n is 1, that's going to be 17 pi over 24. If we add another 12 pi over 24 to that, we're going to get 29 pi over 24. And once more is going to give us a 41 pi over 24. And those should be the 8 locations at which the tangent line to our original function was horizontal on the interval from 0 to 2 pi. All right, a few more to go here. This one, we're just going to find the tangent line's equation at x equals 3. So in order to do that, we just need to take a derivative. Y prime is going to be 2x plus the derivative of natural log of 2x minus 5 is 1 over 2x minus 5 times the derivative of 2x minus 5, which is just 2. And then we'll go ahead and evaluate that when x is equal to 3, which will give us 6 plus 2 over 6 minus 5. Well, that just becomes 8. So now we have the slope of the tangent line, and we just need the actual point for this. So we'll also figure out what y of 3 is. Y of 3 is going to be 3 squared plus the natural log of 6 minus 5. Well, 3 squared is 9, and the natural log of 1 is 0, so that's just 9. So our equation should be y minus that y value of 9 equals our slope of 8 times x minus 3. All right, for our next one, we want the equation of the tangent line to the graph of x plus ln x that's perpendicular to the line with that equation. So first off, let's figure out what the slope of this line is. So we can put that into slope-intercept form, where we can say 6y is equal to negative 2x plus 5, or y is equal to negative 1/3 x plus 5/6. And so the line perpendicular to that, right, a perpendicular slope here, would be m is equal to positive 3. We take the opposite reciprocal. So what we want is the equation of a tangent line to x plus ln x that has a slope of 3. So that means we need to find the derivative here and set it equal to 3, right? Because we want the slope of that tangent line to be 3. So the derivative is 1 plus 1 over x, and we just set that equal to 3. So when we solve that, we end up with 1 over x equals 2, which gives us x equals 1/2. So now we know that x equals 1/2 is the value that we're looking for here. And so we've got the slope of 3, and we've got the x value of 1/2. Now we just need the y value from our original function, which you just plug in a half, you get 1/2 plus the natural log of 1/2. And I don't normally like to write the natural log of 1/2. I'm going to write this. We can always rewrite this as natural log 1 minus natural log 2. And since we know that the natural log of 1 is 0, this is just equal to 1/2 minus the natural log of 2. And it's usually preferred to rewrite natural log of 1/2 as just the negative natural log of 2. So now when I go in here and write my equation, it's just going to be y minus the y value, which was not 3. The y value was the value we just found. Y minus 1/2 minus natural log 2 is equal to the slope, which was 3, times x minus 1/2. And of course, if you really want to, you can put that into slope-intercept form. I probably did on the answer key, but it is not necessary for you to do that. All right, for our next one here, we are just looking for an equation of the tangent line to this curve at the point 1, 2. And since this is an implicitly defined equation, we're going to use implicit differentiation to solve for our derivative. So we'll start off with the derivative of y squared with respect to x, which is 2y dy dx. And then on the right-hand side, we'll have 20x cubed minus 2x. So right off the bat, we can see that dy dx is going to equal 20x cubed minus 2x over 2y, which is the same if we want to reduce that down a little bit in just to make the arithmetic easier. It's just 10x cubed minus x over y. And we need to evaluate this at the point 1, 2. So dy dx evaluated at the point 1, 2. Well, when x is 1, that's just going to be 10 minus 1 in the numerator. And in our denominator, it's just going to be a 2. So our slope is 9/2. And we'll just use point slope form. Y minus 2 equals 9/2 times x minus 1. And that ought to be it for that one. Yeah, we just got 2 more to go. So for this one, we're looking for the potential x-coordinates at which this curve might have a horizontal tangent line. So effectively, we're looking for when does the derivative of this equals 0. And we're only looking for the x values at which that occurs. So we'll take our derivative implicitly, because obviously this is not a function. So that's going to give us 6y squared dy dx plus 2y dy dx minus 5y y to the fourth dy dx is equal to 4x cubed minus 6x squared plus 2x, all just a bunch of power rule derivatives. So dy dx will equal our same values there, 4x cubed minus 6x squared plus 2x. And then the dy dx on the left side can all be factored out, and we'll just divide by 6y squared plus 2y minus the 5y to the fourth. Well, that derivative is equal to 0 when the numerator is equal to 0. So that'd be if 4x cubed minus 6x squared plus 2x equals 0. We can divide everything by 2 if we want, or just factor the 2 out when we factor the x out. So I'll just factor the 2x out. So that's going to give us 2x factored out times 2x squared minus 3x plus 1. And we still want that to equal 0. And so we'll need to factor the inside of that. So to get 2x squared, we're going to need a 2x and an x. And to get a positive 1, we're either going to need 2 positive 1s to multiply or 2 negative 1s. Well, I think it's pretty obvious to get a negative 3x in the middle, we're going to have 2 negative 1s. And since they're both negative 1, it doesn't really matter where we put them. So we're going to have 2x minus 1 and x minus 1. And we'll confirm, right, if we do 2x times negative 1, that's negative 2x. And negative 1 times x, that's another negative x. So that gives us the negative 3x that we needed to have in the middle. And so now, just using the zero product property, we can see that x equals 0 from the 2x would give us a horizontal tangent line. X equals 1/2 from setting 2x minus 1 equal to 0 will give us 1. And x equals 1. And those are our 3 potential x coordinates at which we might have horizontal tangent lines here. All right, and here is our last question. So this is, when does the normal line to the ellipse x squared minus xy plus y squared equals 3 at the point negative 1, 1 intersect the ellipse for a second time? Well, first off, we just need to figure out the equation of that normal line so we can figure out where else it can intersect. So we'll start that off by taking our derivative. The derivative of x squared is 2x. The derivative of minus xy, we'll use the product rule, minus x times dy dx, and then minus y times the derivative of x. And then we'll also have a plus 2y dy dx for our y squared. And the equals 3, its derivative will be 0. We'll just leave the dy dx terms on this side and factor out the dy dx. So dy dx times 2y minus x is equal to a y minus 2x on the other side when we bring those terms over. Dy dx is equal to y minus 2x over 2y minus x. We'll need to evaluate that at the point negative 1, 1, so that we can see what that slope of the tangent line is. So when we do that, y is 1 and x is negative 1, so that'll become 1 plus 2 in the numerator. And then in the denominator, since y is 1, that'll be 2, minus a negative 1, should be another plus 1. So we get 3 over 3, which is just 1. So the slope of the tangent line is just 1, which means that the slope of the normal line, which is the one we're concerned about, is the opposite reciprocal. It's negative 1. And so if we were to write this in a linear equation form, right, we do y minus 1 equals negative 1 times x minus negative 1, or x plus 1. Right? And if you distribute that out, you'll see that you get y minus 1 equals negative x minus 1, or just y equals negative x. So the equation of the normal line to that ellipse is y equals negative x. And so now we need to figure out where does that line intersect that ellipse. Well, a line can only intersect an ellipse at most 2 places, right? It doesn't really matter what the ellipse looks like. Here's our ellipse, here's a line. It can only intersect at a maximum of 2 places, right? And we already know one of them. So all we really need to do is we need to just go ahead and plug in y equals negative x into our ellipse equation, right? We're just using this as a system of equations. We're trying to solve when is this ellipse and this line overlap. So we're just going to plug in negative x for all the y's in that original ellipse equation. So we're going to start off with that x squared. And then we had minus xy, so that'll be minus x times our new y, which is negative x. Then we had plus y squared, that'll be plus our negative x squared, and it was equal to 3. So when we do that, we'll end up with an x squared plus an x squared plus an x squared equals 3, or 3x squared equals 3. And if 3x squared equals 3, then x squared equals 1, and x would be plus or minus 1. Right, well, if we look back over here, we already found the point when x was negative 1. So all we really care about is the point when x is equal to 1. Right? And so we have 2 options. One is we can use just y equals negative x, which in this case is going to be much, much easier. Right? The other option is we can plug it into the ellipse. And I'm going to plug it into both just so we can see, because it has to satisfy both. And this only has one point that satisfies it. Right? So our y value should be, if we're using at x equals 1, our y value will now be negative 1, which means the point should be the point 1, negative 1. Right? And that is our final answer. But we're going to see what happens when we plug it into the ellipse equation too, just because I think it's important to see that. And we're going to ignore x equals negative 1, right? Because we've already got that point, right? And this line is not going to have another point at x equals negative 1, right? Because it's not a vertical line, right? So that's why we're ignoring x equals negative 1. But if we go ahead and plug it in, well, if we use x equals 1, well, our original ellipse equation was x squared, so that'd be 1 squared, which is just 1. And then it was minus xy. Well, if x is 1, that'd be just minus y. And then we had plus y squared equals 3. Well, that quadratic looks like y squared minus y minus 2 equals 0. And when you factor this out, of course, you're going to get y minus 2 and y plus 1, which gives you y equals 2 and y equals negative 1. Well, obviously only one of those is the right answer choice. Right? We know it's y equals negative 1. We already found it from using the much simpler equation to plug it into. But if we'd gone through and done the ellipse equation instead and got y equals 2, we could be certain that y equals 2 wasn't that point, because if I try to plug that in, 2y equals negative x, I'd get 2 equals the opposite of the x value. Well, our x value was 1. We'd get 2 equals negative 1, which is clearly not true, right? And so we would still, again, know that this was the appropriate point. And that is the end of that last question on the equations of tangent and normal line homework. So that's that. That's the end of this walkthrough.